So we continue on Kale. Kale is fantastic. And we are going to study memory. You see, I have a simple and stupid code on which I have some very simple read-write operations. I'm loading a value to R0. And I'm writing that value to somewhere in the memory. Okay, where is that memory location? I'm defining it as a global variable. You don't know this yet, but let me do it. So let me not do it like this. So to keep things simple for you. So this is, let's say that I'm going to use that part of the memory. By the way, you cannot use every part of that memory like this. But I'm trying to make it look like you do because I want you to understand something. So guys, let's do it. That's the simple sound code that you're going to be covering. Okay, guys. So as you can see, I have the code and I'm started debugging it. That's the first line of the code. Let me just go over it. And I'm about to execute this line of code. I'm pressing F10. And I have this value at R2. R2 will be a value, but I'm going to be writing to that value using that value as an address memory, actually, because how do I know this? Because in the following lines of my code, R2 is inside a square bracket, which means it's an index addressing mode. So R2 should be an address value in the data memory because that's how I use it. That's for something I'm deciding. Anyways, so I'm loading another value. Guys, be careful. When I was defining R2, I was using the hexadecimal notation. But for this 1010, I'm not using it. If you are not using it, the language will assume that you are using a decimal number, base 10, not an hexadecimal number. And it's going to write this value to R0. So if you just follow this line, its value will be this 3F2. Why? Because very basically, decimal 1010 is 3F2 in hexadecimals. Be careful about this. This is a trick I do in the exams as well. I want you to be careful about the numbers. This is a decimal number, this is an hexadecimal number, okay? And if you go over this, it just says that it's a 32-bit number, which is like this. And also remember that this is a number in hexadecimal digits of 3 digits, 3F2, only 3 digits. However, I'm writing it to R0 using an LDR command. LDR is a 32-bit command, which means I'm going to be overwriting all 32 bits of R0. How do I do it? I write it to the least significant ones and I make the other ones 0, so that in total, this number is actually 3F2, which is 1010. Now here comes the fun part. I have the yellow triangle here. So if I press 10, F10, it's going to execute it. What is it going to do? Let's do it theoretically first, then let's try to cover this. Guys, sorry. Tuşuna basıyorum ya, alışamadım hala. Okay, this is the memory, okay? These are the memory cells. And these are the memory address locations. You already know that each address location is 8 bits, right? So these cells all have 8 bits, are of 8-bit size. I mean, they can keep only 8 bits. So what this does is you're going to store the value inside R0. Since STR is a 32-bit operation, STR is defined as a 32-bit operation, you're going to read all 32 bits of R0, including the zeros, because all 32 bits I'm saying. And I'm going to write it to somewhere R2 points out. What is the value of R2? It is 2 and zeros. It is like, what does it make? 20 million. It's 20 million. So it's 20 million address locations pointing to that 20 million address location. Okay, so R2 is pointing to this location in the memory. I'm going to be writing 4 bytes because this is a 32-bit location, right? So starting with this address, I'm going to count 4 cells, including that address. So this one is the first one. 1, 2, 3, 4. So I'm going to be writing my total value in these addresses, guys. Okay? So I'm going to be writing the values of R0. I have little endian notation, which means I'm going to be writing the least significant byte, not bit, byte, into the lowest address. What is the least significant byte? F2. So I'm going to be writing F2 here. Okay. What is the next byte? As you can see, it is 03. The next byte is 00. The next byte is 00. Does it really work like this? Well, actually, you have this memory here, guys. You can just, by selecting commands, call stacks, memory, you can click the memory and see a part of the memory. And I'm going to be seeing the memory location starting with 20 million, sorry. So guys, in this notation, since I'm using unsigned char, if you choose unsigned char, it shows hexadecimal 8-bit values for each location, which means, guys, this is 20 million. This is 20 million 1. This is 20 million 2, just like this, 20 million, 20 million 1, 20 million 2. So this is the Kale representation of the bank representation we do. And Kale is fantastic in this manner. If you just, let me just do this like this. If you just move these, so I'm going to be changing the screen. Be careful. So this is 200 to 20 million 1 to 20 million, sorry, 20 million 1, 20 million 2, 3, 4, 5, 7. So 0, 1, 2, 3, 4, 5, 7, 8. This should have been 8, but I'm a bit confused. Is this 8? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7, 8. And it continues with 9. And as you can see, it writes 9. But I'm going to make it bit so it just goes on like this. So guys, if I press 10, I'm expecting that little endianness will work. And I'm going to be writing this value here. I'm writing F10. As you can see, at 20 million, I have this byte. At 20 million 1, I have this byte. At 20 million 2, I have this byte, zeros. And 20 million 3, I have zeros. Okay? This is how you view the memory. And be careful. You designate from which part of the memory this will start. If you make 20 million 1, it will start showing starting from 20 million 1, and you won't be able to see 20 million. That's why I did 20. Okay? Or if you make one number less, what is one number less than 20 million? Can anybody tell me? What is one number less than 20 million? Listening. It is 1.
FFF mi hocam?
Yes,
1
one
FFF.
FFF. So for example, what is less than 20? It's 1 9, right? Because 9 is the last digit. But in hexadecimals, the last digit is F. So it's 1 FFF, FFFF. As you, it doesn't allow you to. I'm sorry, I forgot something. The memory only allows you to show starting with 2 million. So it is, you cannot see it, but just forget it. So you decide from where you start. When you write this number, the first location will be this. So it is like this. Quite simple. We're going to make simple experiments like these, guys. And I'm going to be showing you some other tricks as well. Any questions about this trick? No, I guess. Now, your friend has a question in the chat. He said that he couldn't just move R0 to R1. Let's try to do it. What was the exact question? Let me check. Maybe there's a syntax error. It is, hocam, this one is not working. So let's write it. I'm just copying it, okay? So let's see if this works or not. Build method. One errors. Burada hata var diyor. Neden böyle bir şey diyor hakikaten? Yo. Allah Allah. Ümit sen sormuştun değil mi soruyu? LDR acaba Direct Addressing modda çalışmıyor mu?
Hocam R1'i bir boşluk bıraksak belki fark edebilir mi bilmiyorum. Öyle şeyler düzeltiyor.
İsterseniz yani. LDR. Okay, let me check Ümit. It should, by the way. LDR has a Direct Addressing mode. It should.
Önce sorduk ama öyle bir kullanımı olmadığını söyledi.
LDR'ın Direct modu olmadığını mı söyledi?
Yani öyle bir kullanım
Bakayım
olmadı.
ben. Bakayım ben. Yani these are all about addressing modes, and I thought that LDR has a direct addressing mode. Let me check. Okay, it just confused me. I don't know. Let me check the data sheet. I'm going to check the data sheet. And if Erhan says that LDR doesn't have a direct mode, it probably doesn't have a direct mode. But let me check. Okay, so I get move. But move is 8 bits. Okay, let me check. So let's get back to our examples in the memory. So guys, I'm going to teach you something now. I'm going to be defining a new version of STR and LDR, which are LDR was 32 bits, right? I'm saying that LDR H is the 16-bit version. And STR is also 32 bits. I'm saying that STR H is the 16-bit version. What I'm trying to say is, I'm going to change this code, guys. I'm going to make this code as LDR H and STR H. In this case, it's going to work for only 16 bits. Let's see how it works. Hala hatam veriyor bu. Nerede hata veriyormuş? Ha, okay. Bu niye ya? Ha, LDR H, bir saniye. Allah Allah. LDR H'im beğenmedi. Ha, LDR için direct modu yok. Immediate modu yok. Okay, I just realized that LDRH doesn't have an immediate mode. Don't worry, we are going to use the SDRH. So I guess it is this. Okay, don't worry. So we are doing this example. I'm saying that LDR is 32 bits. I'm using SDRH, which is 16 bits. What will change? Since this is 16 bits, what's going to change is, before we run the example, let's stop here. So I'm going to be drawing the same things. So guys, there's a memory here like this. Okay. And this memory address is 220 million, sorry. So 1, 2, 3, 4, it goes on like this. So this is the place. What I do is I write a value inside R2. So when you do this, you have the value inside R2. R0 is 3F2. Now what I'm going to be doing is I'm going to write the value inside R0 to R2. And STRH is a 16-bit operation. 16-bit is 2 bytes, 2 8-bits. So it's going to be covering only 2 cells in the memory, which means I'm not going to be using 4 cells, but I'm going to be using only 2 cells in the memory, these 2. And I'm going to be writing the least significant values to these 2 cells using the little endian. So in R2, let me write it here. So what was the value of R0? R0 was right? As you can see, that's secure. So guys, since STRH is reading the values from R0 and writing it to the memory, and since STRH is only 16 bits, I'm going to be using only the least significant 16 bits here. So forget this part. I'm not going to be using it. And since this is a 16-bit, it's going to be using 2 cells in the memory. So this time I'm going to be writing F2 to the least significant lowest address because it's little endian still, F2, and 03 here, but not changing these values. In the previous time, we have written, since this was not STRH, it was STR, I've made these 0, remember? And we have written them accordingly, and these bits were 0. Let's see if it happens again. So I'm going to be writing this. So F10, as you can see, this one, these ones didn't change because STRH did not change that part of the memory because it's a 16-bit instruction. It only affected 2 cells in the memory. So we make a new definition. The instructions are either 16-bit and 32 bits. Okay? So depending on their definition, we are going to change the memory. STR is by definition 32 bits. STRH is by definition 16 bits. Any questions about this? I guess not. So let's make another example. Var mı kusur arkadaşlar?
Hocam ufak bir sorum var.
Lütfen.
STRH yerine STR kullanmış olsaydık diğer alttaki iki memory seli de 0 mı yapacaktı?
We did it. The previous example was exactly like that, and that exactly happened. Don't you remember? Actually, yes, we did that example. And yes, it happened that way. Okay?
Hocam
Hı hı.
burada hani STR parantez içerisinde R2,4 yazdık ya.
Hı hı.
4 tane alan mı ayırdık R2'nin içerisinde?
Can you repeat the question?
Şimdi hocam hep 4, 8, 12, 16 diye gidiyor ya. Sürekli
Hı hı.
4 bitlik bir yer mi ayırdık R2'nin içerisinde? Mesela 98'e yazabilmek için R2'nin içerisinde 4 tane alan mı ayırdık? Sizin çizdiğiniz kutularda hep, sizin çizdiğiniz şekilde hep 4 tane vardı.
Okay, but yes, because it's 32, because the example, well, in the previous example, it was only 2 cells, not 4 cells, because it was STRH. Okay? In the previous example, it was 4 cells. Because we have not used STRH, we have used STR, which is 32 bits. And 32 bits is, how many 8 bits does it make 32 bits? 4 8 bits make 32 bits. That's why it's 4 cells, because each cell is 8 bit.
Tamam hocam, sağ olun.
We are going to make examples and it's going to just, settle. And please rewatch this lesson. It's going to help. I'm going to make a tricky example now, guys. I'm going to be writing a complete value, not like this, maybe just like this. This value. Can I write this value? Yes, like this. And it has values more than 2 bytes actually. But I'm going to be using STRH to write to the memory. So what's going to happen? So can you see what's really happening? I'm going to be covering what's really happening. So this is the same example. So let's change some things in the example. So I'm sorry, I'm going to change. So I'm going to make this. To make things, I'm going to use another memory location. Okay, so I'm writing to that part of the memory. Okay, so R2 is this value. And R0 is this value. Okay, now I'm calling this. What is going to happen? Let's first speculate. So we have the memory. Imagine this is 20 million. This is 20 million 1 in hexadecimals, of course. 20 million 2 3, 4, 5, goes on like this. So this STRH is going to read values from R0. It's going to write them to the memory where R2 points. Where R2 points is this time this, because we have this value here. Okay? And it's going to write the values inside R0 in a little endian manner, which means the least significant byte being written to the lowest address. And since STRH is 16 bits, it's going to be using only these two locations. Okay? No more, these two locations. And what is it going to write? It's going to write first the least significant byte, which is 098, and the next one is BA. Well, what about it? I've got other values. Will they be written? Let's see, guys. Let's see if they are written or not. Because I've got the memory here. And I make jump. As you can see, it only write these two. It didn't get the value DC because STRH is a 16-bit operation. STRH will only touch two cells in the memory because that's its definition. If you want to write the entire number to the memory, you have to use STR, guys, not STRH. Let's do the same example using STR this time. Okay? So I've changed the code. I'm going over it. I'm loading the code. I'm doing it again. So it is here. Let's come. So as you can see, let's see what's going to happen. This time, this is STR, which means it is going to write to 4 bytes. So if you put it this way, it's going to be all these 4 bytes, guys, starting with this location, because that's the location of STR. So it's going to be DC and 00, 4 bytes all, because this, although you have 00s here, since STR is 32 bits, it's going to write them all to 4 bytes. So as you can see, this is the memory. This is 20 million. This is 20 million one. This guy, so these locations will change, guys. Be careful when I change them, okay? So I'm going to jump the code, and they are going to be changed like this. As you can see, they are changed. That's how STR and STRH and the bit size of an instruction works. Any questions now? Okay, very good. We are going to see these and work on these a lot, but I'm going to be teaching you some other instruction. There is STRB, guys, which is only 1 byte, which is 8 bits. Very similar to these, but it only transfers 1 byte. So let's do it. Let's do this STRB. So what happens is quite similar. So I'm saving my code, rebuilding my code because I have to rebuild it. I've changed the code. I load it. I just work on it. I start a jump. So it is the same. So this is STRB, guys. It's 8 bits. It's only going to change one memory location. And I'm not going to draw the entire memory location, but I'm going to show it to you. This is 20 million, but this will be doing an operation starting with 20 million and 1. So only this guy will change. These won't change because I'm using STRB 8-bit single cell operation. So does it really work like that? And which single byte? Which single cell? Because of little endian, lowest address will be written to the least significant bit. So this guy will be 98 only, the others won't change. This is how we change the memory. Write and read over the memory. Any questions? No, I guess. So guys, I'm going to make another test about the stacks. So before I finish today, I told you when I was talking about stacks, don't care where stack is in the memory. I always said that. But actually, you can check that part of the memory. How? I'm going to write another piece of code, add another piece of code here. For example, I'm going to be pushing R0 to the memory. So what happens? Let's elaborate. Let's just work on it. This is also a good example for us. Now, let's jump. Let's do these operations and STRV and this. So what it's going to happen? Actually, you know what's going to happen. There's a place in the memory where I call this stack pointer memory, stack memory, or. But now you know that memory locations are 8 bits. So stack pointer is pointing to somewhere. Okay? Stack pointer is pointing to this place. And when I run this code, the values inside R0 will be written to the memory. But the memory locations are of 8-bit cells, and R0 is 32 bits. So most probably, it's going to be using some 4 cells in the memory, and write that value to 4 cells in the memory, and move the stack pointer accordingly. Does it really work like that? Actually, I can check. The value will be written somewhere in the memory where stack pointer points us, right? Where does stack pointer points to? Do you have any idea? Can anybody see it on the screen? I'm moving my cursor there. This is the stack pointer. Actually, that's a place in the memory. So let me look at that place in the memory, guys. Let me just look at that memory in the. So I'm writing the exact same value here. So it is the start of my stack memory. This is this value, this value, this value, and this value. So I'm going to be running this code. Biraz daha gerisi miydi o? Evet, gerisiydi. Yes. Let me just. I'll do the example again. Sorry. Okay. Okay. So I run. Sorry. So I'm going to write somewhere in the stack memory, and stack pointer is showing to this place. Stack pointer showing to this place. For some reason, I'm going to point 4 cells before, okay, which is this location, okay. So guys, it is to 20,424, 25, 26, and 28. So 24, 25, 26, 27, and 28. Actually, stack pointer is pointing to this location. Stack pointer is pointing to this location. Sorry, not this location. This location. Stack pointer is pointing to this location. Any questions about this? Because it's written here. Stack pointer is pointing to this location. So guys, actually, when I was drawing the theoretical design of the stack pointer, it did not exactly match. Now I'm going to be making another notation, which is going to match actually. Stack pointer is actually pointing to the location where you will write before. So if stack pointer is pointing to here, this is an address, and that address is actually written as the stack pointer address, which is 228. I've taken this from here. It means that the next value to be pushed will be written to here. This is 28, 26, 25, 24. So these are decreasing. Don't worry about it. You can draw it any way you like. So if I just make the push, as you can see, the value inside R0 is written to this address in a little endian manner. The lowest byte written to the lowest address, next one, next one, next one. And the stack pointer now is pointing to here. So it's not pointing to here. Let me change my drawing. Now the stack pointer is pointing to here. Pointing to here. Just like in my example, stack pointer is pointing, sorry. Stack pointer is pointing to here now. Stack pointer is pointing to here. So it is. So stack pointer is pointing to here now. So guys, when I push something else, it's going to be written to these parts. Go on like this. So in this notation, I've drawn the addresses as decreasing, but don't worry about it. You can draw it any way you like. So actually writing to stack pointer is writing to the memory. It's no different than that. So when you write something to the stack pointer, actually you can check it. If you have really written that value, you can check it. And stack pointer push always pushes 32-bit values. Any questions? I guess not. You can just write any value here to check the memory.
Hocam ben sadece şey soracağım. Önceki örnekten bu sefer farkımız da önceki örnekte sadece hani BA ile 98 kısmını alabilmiştik ya. Ama kod aynıydı.
It was not. We are using push here. Are you comparing push or STRB? I mean, if an instruction is 32 bits, it writes to 4 cells. If it is 16 bits, it writes to 2 cells. If it is 8 bits, it writes to a single cell. Okay? Push is 32 bits. STRB is 8 bits. STR is 32 bits. STRH is 16 bits. Okay?
Okay.
Okay, that's it. Okay, now I've been talking about this pointing to memory. So stack pointer is pointing to memory. R2 is pointing to memory. So guys, actually, if you need to write something to the memory, you need pointers, guys. So these are called the pointers, just like in this example. In order to write to memory, you are using index addressing or stack pointer. So you need the address of the memory to be written to a register. These registers are used in these index modes, or the stack pointer itself are called pointers. Actually, you have pointers in C++. That's exactly the same. If a variable, if a register is telling you a place in the memory, that's called a pointer, guys. Okay? A pointer is a programming language object that stores the memory address of a value, okay, in the memory. A pointer references a location in the memory. And you can get the value. In our memory, each cell is 8 bits. So if a pointer is pointing to 32-bit value, which means go to that address and count 4 cells. If it is 64 bits, go to that address and count 8 cells. So we know that since R2 is a pointer, it's used in index addressing, it carries address data. We defined R2 to be a pointer. Okay, this could have been data as well, but this is address. I know because I've defined it. I've put it in an index addressing mode brackets. It is us that knows R2's values and address, because this question comes always. Hocam, how do we know that R2 is an address or a data? Well, you decide it. Don't ask me. You are writing the code. And if you're reading somebody else's code and trying to understand if certain register value is an address or data, if it is used inside the bracket parenthesis, this square bracket parenthesis, it must be address, because that's the index addressing mode. But R2 is still just a register. It's keeping data. R2 itself doesn't know this. We know this. We define it to be a pointer and use it to point somewhere in the memory. Okay. So this is an example. This is just like the example we have done. Okay, before I continue to new objectives, I think that's it for this week's content. Any questions?